Hi everyone, I am Igor. I'm very glad I get to present these results in this very nice conference in this very nice place. So as you heard, I am from Institut d'Optique in the quantum optics group, where we're more atomic physicists than quantum opticians. But we have an activity on collective light scattering, which connects to quantum optics. So this is what I'm going to present today. So what we do is that. Bah, alors, ça marche plus. Okay, let's do it like this. What we do is that we're able to isolate essentially a two-level system in an atom, and we know how to interrogate it with light. We know how it responds. You all know that. You know the optical block equations, and essentially the question we want to ask is now. I know the response of a single atom, but what is the response of many atoms that I put together in free space? So in this talk, there will be no cavity, no waveguide. It's just atoms in free space. So you will see that you have a very collective response. As a matter of fact, when your atoms are close to each other, and of course, it's not an easy answer. There is no easy answer to this problem because it's a many-body problem. You have an ensemble of two-level systems, so you have many qubits if you want, and you have to solve a many-body problem to understand it. So you know probably that there are some approximations you can make, like Dickey, who said that now if you take a very symmetrical problem, you can reduce the complexity to a small number of states, and then you can solve the problem. But in all generality, it's very challenging. But it's interesting to study. Why is that? One motivation in our field is that we are able now, as we heard, to create quantum simulators out of single atoms, and these are made of many atoms in free space. Okay, and we have to interface them with light to make interconnects, for instance. And so understanding now the many body response of an array of atoms is important. First of all, to be able to extract information, for instance, or maybe to use collective effects to enhance light matter interfaces. Maybe you've heard about the possibility to make a mirror out of single atoms in free space, and there are many other possibilities. Uh, Another reason why we should study this is that when you perform metrology, if you have an optical clock, what you do is that you send resonant light on a bunch of atoms in free space. And so if the collective response is modified by collective effects, if the field of atoms in the clock actually act on the other atoms and modify the response, you might have an uncertainty on your clock. So you at least have to understand the problem in order to mitigate these effects. And it's also an interesting quantum many-body problem. This is our background. We're quantum many-body physicists, and so solving this issue and trying to understand it is interesting per se. So, what does it mean understanding collective spontaneous emission, or the collective response of atoms to light in terms of the atomic state? Essentially, when you measure the light that is emitted by two atoms, you're measuring the intensity with your detector. And say you have two atoms, then you're measuring the field that is radiated by these two atoms. When you're in free space, it's possible to show that actually the field that is radiated by the atom is given by just the dipole operator. Okay, so it's the if you have a classical atom is just an oscillating dipole. If it's a two-level system, you have to take this operator, which is the lowering operator that acts on atom n, and you just propagate the field. This is the Green's function of the field. You propagate the field from the position of the atom to the position of your detector. Okay, so in the far field, the Green's function looks like this. So when you're measuring intensity, you have to sum over all the different atoms. Okay, and what you get is a double sum where you have a sum over correlations. Okay, so this gives you actually two probes as an experimentalist to look at this problem. One is that you can look at the radiated field, like I showed here. Okay, and this radiated field depends on correlations in the sample. Okay, what you want to understand eventually is maybe what is the field that is radiated by the atoms. Okay, but in order to predict what the field is going to be, you have to predict what are the correlations. So here it's for intensity. When you have a higher order, if you want to predict second order coherence, for instance. It's not a two body correlator, it's a four body correlator that you have to calculate. Of course, it's extremely challenging to do because you have an ensemble of qubits. Okay, you have to solve the many body problem, so it's impossible. Of course, you have to make approximations in order to predict these atomic correlations. And for us experimentalists, this simple expression is interesting because it shows that we have two possibilities, two ways to look at the problem. One way is to look at the field that the cloud radiates. Okay, so you place a photodiode, you place a camera, and you look at the field that is emitted. Or another way is to look at the internal degrees of freedom of the atoms, and that's something we know how to do now, thanks to recent developments in atomic physics. We're able to measure the state of single atoms. Okay, and actually in our group we have two experiments where we can probe these two aspects. We have a first experiment. You've heard about it in Sarah's talk on Tuesday, where we make dense ensembles of rubidium atoms. Okay, and there we use the fact that we have many atoms, and rubidium, we use a transition that's rather broad, so we can emit and collect many photons. So we look at the radiated light as a function of time, for instance, on this experiment. This gives us information on correlations, but then we have another experiment where we prepare ensembles of single atoms where we have access to every single atom in situ. We can measure in a single shot the state of the atoms in order to trace back, for instance, what correlations are in the system. So right now we've set up the experiment, and we're able to access the atomic state, and I will show you a tiny experiment where we can measure collective effects by looking at the internal state of atoms. So let me first motivate a little bit what we're doing, and show you what you can do when you measure the radiated light. So the work that I'm going to show you has been done by this team, and Sarah has showed you how she has built a new experiment to explore these problems again. The results that I'm going to show you are on the previous version of the experiment, where we trap dense clouds of two-level atoms, rubidium. We isolate. She showed you how we isolate a two-level transition. Okay, and we make these ensembles that are particular because they have a radial size that is small, with the order of the wavelength. Okay, so you have something that's smaller than the cross section for the interaction of a photon with an atom, but along the axis, the size of the ensemble is rather long. And so essentially, when you calculate, you try to make a phased antenna array, for instance, out of this ensemble, and you ask whether you can have constructive interference. Then actually there is a single direction in which you can have constructive interference. There is a single mode along the cloud axis where you can have collective emission of light. If you try to uh, have atoms interfere in any other direction, it's impossible. Another way to look at this is, if you emit a photon along the cloud, then there is no way to know which atom emitted it. If you emit a photon perpendicularly to the cloud, actually you can trace back a region where the atom, the photon was emitted. And so this allows us actually to define, by comparing how much power you can emit in the collective mode and how much power you emit independently in 4 pi. This allows to define what people call the cooperativity. So this would be, for instance, in a cavity, you compare how much you scatter in the cavity mode with respect to 4 pi. This is the cooperativity. In our case, this cooperativity is small if you have a single atom. It's negligible. But when we put many atoms, we can have a cooperativity that's larger than one, which means that we can have enhanced scattering in the mode. In particular, we can have super radiance as I will show you. So this cooperativity in another language is optical depth. Okay, and we get optical depths up to maybe 10 at most. Okay. Uh, so here is what you observe when you now scatter light off of a bunch of atoms. We have access by looking at light that's perpendicular. I don't have time to explain you why, but we have access to the population as a function of time. So this is an average over many shots, not single atom resolved, but we can still see as a function of time, the population oscillate. And this is just Rabi oscillations that decay because we're looking at something that radiates. We're interested in light radiation. So these Rabi oscillations decay, and you see that this matches very well predictions of optical Bloch equations as a dashed line. Okay, so what this tells us is that we can prepare different states, and in particular, we can look at what happens when we invert fully the ensemble. Okay, so we put everyone in the excited state. That's what you get when you stop your drive here. Okay, so if we stop the drive here, essentially we've excited all the atoms to the excited state. And if you know a little bit about superradiance, you know that this is the problem that Dickey has studied. Okay, and what's predicted in this case is that you have a pulse of light that is emitted, an enhanced spontaneous emission at a much higher rate than single atoms. Okay, that's due to constructive interferences and the fact that the atoms spontaneously get in phase with each other and start to send coherent radiation. Okay, so in our cloud, of course, we're not in the case of Dickey, which was extremely simple. It's an ensemble in free space with finite size, whereas Dickey looked at something that was all atoms at the same position. But in fact, it's known for a while now that you should have superradiance, and thanks to our detection now along the cloud, we know that for our cloud, superradiance should occur only along the cloud, and we detect these pulses of light. If you look at as a function of atom number, at low atom number, we have an emission per atom which is constant. Okay, for two different atom numbers, we get the same number of photons emitted per atoms. And then all of a sudden, you reach a threshold for superradiance and you see a bright pulse of light that is emitted. And this bright pulse is exactly Dickey superradiance. What's interesting for us as quantum many-body physicists is that actually, if you want to describe this problem, it's not easy. You cannot make a simple mean field approximation. Uh, you have to make better approximations. You have to account for these types of correlations that are not there in mean field theory and that are at the heart of Dickey superradiance. So we teamed up with Francis from Purdue, where he used a cumulant expansion for the experts to describe this problem, and it worked very well for us. So you see that we're starting to see many body effects. Then the next thing we can do is to say, okay, what is a second order coherence of light in superradiance? Okay, you look at a superradiant pulse and you ask now what is G2 of tau. Interestingly, superradiance is known since the 50s by Dickey. It's been observed in the 70s, in the 80s, but no one had ever looked at what is G2 of tau during a superradiant pulse, because it's rather actually challenging maybe to have single photon detection. But nowadays with the modern techniques, it's not very hard. You make a Hembury-Brownlee twist setup, and what we have observed in our experiment is the following. I have to get closer, closer, closer. Okay. Yep. Is that if you start at the end of the pulse where you fully inverted the system, actually we have some dynamics during the pulse. So the dynamics begins before the end of the pulse. We see a G2 which is close to 2. It's not. We have a big uncertainty, but it's relatively large with respect to 1. And what this tells you is that essentially when you have independent emitters in free space that just scatter light independently, what you expect is Hembury-Brownlee twist. You expect G2 is equal to 2. Okay, and then as a function of time, we see that the G2 of the light that is emitted by the cloud goes to 1. And this is really at the essence of Dickey superradiance. Is initially you have emitters that are completely out of phase with respect to each other. They emit independently, and you have a G2 which is equal to 2. And then they phase with respect to each other. So they are coherent, and you send a coherent field. Okay, and we observe the buildup of coherence as a function of time. And what's interesting here is that there is no theory. So it's too hard to describe. Now you have to go to fourth order in correlators, and so far no one has been able to describe this. We can make a very simple estimate by mapping this into a very simple Dickey model with an effective atom number. We have a qualitative description. Okay, in Dickey superradiance, you expect that it goes to 1 as a function of time, but we don't have any better understanding. So that's a motivation to say, okay, now it seems that it's extremely challenging to predict these correlations. So let's go and build a system where we can actually measure these correlations in situ, measure, have access to the atomic state, and that's the motivation for this new platform, which is based on single atoms of dysprosium that I will show you in the last 10 minutes of the talk. So here, the work has been done by this group of people at Institut d'Optique. So we have built a cold atom experiment, a single atom tweezer experiment based on dysprosium. We have heard actually one talk about dysprosium in this conference. You've seen that it's a relatively complex atom. So here is the atomic structure. So some of the states. So it's not an alkali. It's not simple, but actually nowadays it's an atom that has been trapped for a while, and we understand better its atomic structure. And in fact, the advantage for light scattering is that you have access to many different transitions with different wavelengths and different line widths. So here is an example of three possibilities that you have with dysprosium. It's very similar to erbium, for instance. All the lanthanides have this rich structure, and you see that you have many different. You have really orders of magnitude difference in line widths, and you really have uh, a broad choice of line widths and wavelengths that you can pick. So this means that, for instance, you can decide to scatter light on a relatively narrow transition, okay, one of these two, for instance, and you can use a very broad transition to measure the atomic state. Okay, so measuring the atomic state is something that people do on a daily basis in quantum computing, for instance. What we want is to have a two-level transition where we can do light scattering, where the light width is not infinitely short, but where we can still measure fast enough the state of the atom. So this is the challenge that we had to overcome. So first of all, we needed to build a single atom dysprosium experiment. It's a relatively standard thing, a standard experiment nowadays to have single atoms in optical tweezers. It was never done for lanthanides before, but we adapting known techniques, we were able to have single atoms in optical tweezers. So you see here we have a microscope objective that focuses optical tweezers, and in each of these optical tweezers you have one atom, or you have zero when you start loading the ensemble. And by imaging the focal plane on the camera, you can image the atoms. The technique to sort the atoms has been developed years ago now for special quantum simulation and quantum computing. So we can use these techniques. We have a 2D acousto-optic deflector, and we can merge, for instance, a randomly filled array of traps into a perfectly filled chain. Okay, and so what I'm going to show you today is uh, what happens now if you just play with an ordered system, a very simple 1D system, and you scatter light off of it, but now you measure the atomic population rather than measuring the light that has been emitted by the cloud. So to isolate a two-level transition in dysprosium, we've picked this transition. It's relatively narrow, so you don't need a very strong magnetic field to isolate a two-level transition. We have J is equal to 8, so we isolate the two stretch states, the two lowest states. Mj is equal to -8 and -9, okay? And you can ignore all the other Zeeman states when you perform the experiment, as soon as you have even a very small magnetic field. And then we just scatter a resonant laser off of this chain of atoms, and we probe what happens. How do they collectively absorb light? What is the excited state fraction, essentially, of these atoms? So how do we measure now the atomic state? Okay, we scatter light, but as I told you, I'm not going to look at the photons that are emitted. I'm going to look at the atoms. So how do we do that? Well, we use the fact that we have another transition. So you scatter light and you put some atoms in the excited state, some atoms in the ground state, and then we use the very broad transition that has a line width of 32.5 megahertz to another excited state, and this one can depump very fast atoms out of the ground state. Okay, so this can happen in 100 nanoseconds because the line width is so broad, and these 100 nanoseconds are very short with respect to the lifetime of the excited state. So what happens is that they move out of the ground state while these ones are still in the excited state. This is well known in ions. This is called shelving. In our case, we have to do it extremely fast because we're interested in the dynamics on this transition. So the dynamics is not infinitely long. We have 1.2 microseconds to do that, but it's long with respect to the 100 nanoseconds it takes. So actually, we can remove the ground state atoms, and then we can let the atoms that were in the excited state decay to the ground state, and we measure again. And the ones that we measure are the ones that were in the excited state. So when we measure an atom, now if it's here, it was in the excited state. So we can project and measure the state in a single shot on every single atom to measure now what is the state once the chain has a scatter light. The fidelity for this readout is limited by the ratio of these two times, and it's about 92%. Okay, so here is, for instance, now Rabi oscillations that I showed you before, but now we're not looking at the photons that are emitted, but we're looking at the excited state fraction, and you see these Rabi oscillations that decay due to spontaneous emission, which is what we're interested in. We want dynamics of light emission on this transition, and you see the readout. So we're able to transfer a very large amount of atoms to the excited state, for instance, and we have a good fidelity for the readout. So now, once we have this tool in at hand, what happens now if you measure the population when you scatter light, when you shine light on a chain of atoms? Actually, this problem was looked at by Francis Robichaud, the same guy with whom we collaborated, and his student, and we actually looked at this problem in a 1D geometry, but not in an ordered chain with rather disordered cloud, a very elongated one. Here we are now looking at a chain of single atoms in free space, and we send light. For instance, let's send light along the axis and look at what happens. So to have an intuition, actually we can think of how light, what happens to light when it scatters off an atom and reaches the end of the chain, for instance. So you have your driving laser. Okay, this driving laser might drive this atom. Okay, so what you pick up is a propagation phase, which is here. Then actually what you when you scatter light off of the atom, you have a phase shift that is the that is the phase that's given by the polarizability of the atom, and then the atom radiates a field. Okay, and this field propagates to the next. Okay, and so when you add up these two phases together, what you see is that actually the phase here, the total phase, doesn't depend on the position of the atom that scattered the light. It's a very simple effect. Any atom that scattered the light and sent it to the end of the chain gives exactly the same phase. So the radiation from all atoms at the beginning of the chain is in phase. It constructively interferes towards the end of the chain. Okay? So basically, when you look at the field at the end, you just sum the laser field. So that's this one here, and the field radiated by all the other atoms. And now these two fields, the laser and the atomic field, might be in phase or out of phase with respect to each other. That's given by the polarizability of an atom. That's given by the response of the atom. And here it's just a simple harmonic oscillator. If you drive it from the rate of the resonance, then you have no phase. It's in phase with the field. If you drive it out of resonance, then you're out of phase. So either you have a constructive interference between the laser and the atomic field, or a destructive interference. And this is what we see experimentally now. If you shine the laser and you look at the atomic population now, a single atom resolved on the chain, it's noisy, but we see a growth of the excitation in the chain if we are red detuned, because these fields interfere constructively. And when we are blue detuned, we see now an absorption, a little bit like Beer-Lambert law, but at the level of single atoms when we are blue detuned. So now, how do we understand this? Why the title of these slides is the cooperative lamp shift. Actually, the cooperative lamp shift is what people call the shift that you get, the shift of the transition that you get due to collective effects, due to dipole-dipole interaction in an atomic ensemble. And here we understand very well now, by looking at the microscopic, we understand very well how this shift happens. You see that when you're to the blue, you reduce the excitation probability. When you're to the red, you enhance the excitation probability. So you have a shift towards the red of the transition. Okay, so we observe this shift now. We understand it very well. Uh, in the interest of time, I think I will just go very briefly about the fact that this shift here is exactly the same shift that you get in an optical clock. Okay, it's an interesting exercise to make, that you try to calculate this shift, whether you're doing it by driving the atoms in a steady state or performing a Ramsey experiment. You get the same shift, except that in a Ramsey experiment, it depends on the excuse me, on the area of the Ramsey pulses that you make. It's been observed on an extremely narrow transition in a paper by Juni's team at GILA. They observed this shift, and in our experiment we also observed the same shift in a Ramsey experiment now, and it's an interesting platform, because actually on an optical clock you can't look at, for instance, spontaneous decay. It's a millihertz transition, so you don't have time to wait 1,000 seconds. Whereas in our case, we can look at the dynamics of the Ramsey experiments. So with this, I will just summarize. So we have two experiments in our group where we look at collective light scattering. One where we're interested in the light that is emitted, and one aspect that we would like to push further is whether it can be an interesting platform for quantum optics. Can you use these collective effects for interesting quantum states of light? And on the other platform, we've set up the ability to measure the atomic state. So far, we didn't measure correlations. We just looked at a simple collective effect, but now we have the basis to look at correlations. And with this, thanks for listening, and I'm happy to answer any question.
Thank you very much for this enlightening talk. Other questions? Yeah.
Thank you very much. But I just missed the point, because you say you want to study correlation in the decay regime, and in your dispersion chain, you are not in the decay regime at all.
So I didn't say I wanted to study it in the decay regime.
Okay, so because you say it's not, it has not been studied in.
So essentially in the decay regime is an interest. I mean, it's you can solve it on your laptop for 10,000 atoms if you want. There is no difficulty. So the interesting many-body physics arises when you have something where the atoms are close to each other, but not infinitely close. Right now on the experiment, the distance between the atoms, I didn't say, is larger than the wavelength. So that's why we have this very simple mean field effect. Now we are gearing up the experiment to go below the wavelength, and below the wavelength, this is where you expect to have non-trivial correlations that are beyond mean field. As a matter of fact, if you do the math properly and you do beyond mean field theory, the effects, even in a chain that has a distance larger than the wavelength, are non-negligible, and you can already look at many-body physics in let's say in a regime where the correlations are controlled, and you can compare it to theory.
Then I will have a small experimental question, because you observe into like 620 nanometer transition, so you need to go below in resolution. Like, so you go with your tweezer, or do you?
No, so there are two answers. So the first one is we can use other transitions. It's just like in erbium, you have many other wavelengths, and then with tweezers you can take two tweezer arrays and intertwine them, so you can get below the wavelength with this. You won't get super deep, and then we need to load an accordion lattice with a high NA objective to go below 400 nanometers.
Okay, thanks.
There's another question over there.
Thank you for the nice talk. So you say you want to measure correlations, like with the tweezers, with the second experiment. How would you pump the atoms, and or like how would you probe the atoms, What do you expect to see, like anti-bunching or
It's
rather
a
super radiance also? Or,
it's a very good question. So for instance, you take a chain like this, you do the same. So you pump, you drive the atoms to the steady state, for instance, and in steady state, due to due to collective light scattering, you have non-trivial correlations. So if you measure now uh, um, sigma z, then you can show that you have beyond mean field effect in the sense that it's not equal to the product of the average. Okay, you more interesting, you should look at the dipole actually, so you can change the basis in which you measure to measure sigma x or sigma y, because it's an xy interaction in this case. Another aspect that theory has looked at is you start from a fully inverted ensemble, you let the ensemble decay, and at very long times, if you have excitations that are left in your ensemble, these are subradiant excitations where actually you have destructive interference. And if you try to understand how do you construct destructive interferences between atoms where you have two excitations in your ensemble, then actually you can show that you expect non-trivial correlations that are of the fermionic type. You expect fermionic correlations, and that you can probe also by measuring the excitations, and you can measure sigma z again in this case.
Thank you.
Welcome.
So we need to move on, unfortunately. So let's thank
Thank
the
you.
speaker again.
Yep.